Let's study what I just explained before, which is the filtering trade-off between the computational time and the kind of filtering that you can do for a specific constraint. And for this, for explaining this trade-off, I will use a very simple constraint, which is x equal to y plus 1. Assume that the domain of x is 1 to 9 and the domain of y is 0 to 8. Okay? And so I will represent on this axis, on the y-axis, the domain of y, and the x-axis, the domain of x. And all the feasible combination for x and y is represented here with a yellow point, okay? Because x should be equal to y plus 1. And so you've got this line here with an offset of 1, okay, with an intercept of 1. But of course, you're interested on the discrete combinations here because the domain is also integer. Assume now that some values inside the domain disappear. And so we are in this situation with some sparse domains. What kind of reasoning can we do to filter further the domains? The kind of reasoning that we will do is that we will do a projection of the set of solutions on the x-axis and on the y-axis. And so if you do a bound reasoning, so you will really focus on the bounds and you will consider that the intermediate values are not really removed. You will do this kind of update. Okay, you will say that the minimum of x is equal to the maximum of the minimum of y plus 1 and the minimum of x, and similarly for the maximum of x. Okay, and so you will update it like this, and project. You will project it here. And so you will get rid of these two sets of values, the values 1 and 2 for the domain of x. And similarly, we will get rid of the values 2 and 7 and 8 for the domain of y. Okay? But you could do something more powerful, which is also reasoning in terms of removed values inside the domain. And in that case, you will also be able to remove the value 5, for instance, from the domain of y. And you were not able to do this in the situation before. Okay. Of course, this is a little bit more costly because you cannot apply very simple formula like this one. Okay. You see that applying this kind of formula, of course it's valid, but it's also very easy to do. It can be done in constant time, right? It's just a basic arithmetic operation, computation, based on the bounds of the domains. If you want to do this kind of reasoning, you really need to look inside every values of the domains, and this is more expensive. It may take something with a time complexity that is in the order of the size of the domain of x. Okay, so this is more costly. This is not really constant time. This is not necessarily constant time. Okay. And so it's always a trade-off between the computational speed that you want to spend in every constraint and the kind of filtering that you can do. Okay. So this is a trade-off. Let's consider the very easy update, and let's see how to implement this inside MiniCP. And as a programming exercise, you will have to implement your own constraint also today. So I want to implement here the constraint x is equal to y plus 1. I will extend for that the abstract constraint object, abstract constraint class, which is an abstract class. And I will need to implement the post method. And so this, you see that I'm overriding this. I'm posting this. Here I'm really doing the hookup of the constraint with all the callbacks. I will say I want to do the bound intersection every time the variable, the domain of the variable y changes. I want to do this. Okay, I want to do the bound intersection. When the domain of x changes and when the domain of y changes, I want to perform this. And this is really the bound update. So what it means is that during the fixed point computation, this piece of code will be executed every time the domain of x changes and every time the domain of y changes. Okay, this is how it works. Okay, we also call this a lambda function because you see that it's really a closure inside Java, I capture a piece of code that will be executed later. I will store it, and it will be executed later every time the domain of X changes and every time the domain of Y changes. Okay, so again, if I come back to my trade-off between the filtering levels, you might imagine that you have a strong or a weak filtering. And unfortunately, depending on which one you choose, if you have the choice between the two kind of algorithm, you might end up with a small search tree or a large search tree. But the small search tree doesn't mean that it's executed faster, because if it's small but you spend more time inside each node, it's not always the case that the total size, the overall time that we'll spend for solving the problem is also shorter. Okay, so which one should you choose? The strong filtering, which is slow, or the fast filtering that is a little bit pruning less? It really depends. It's you should experiment a little bit with your problem. It's not a trivial question to answer. In the next video, I will explain how constraint programming can solve optimization problems as well.